taking time and spending it this way. We'll try to do something useful, and for folks who come in a little later or can't make it, Luz, you are recording this? Okay, yep. So that's started. Okay, well, we also have somebody not on the Zoom call, but Mr. Bill is also attending, and so he's here to check in on us from time to time. And let's see, I've got materials that are posted to a Google Drive, and I'm not sure, I saw Ernesto is also moving materials to a sociology department webpage. And so I think that means that they're in two places at once. I move my materials first to the Google Drive, and then Ernesto moves them over to the sociology webpage. I've put the slides for today's presentation on the Google Drive, but they're not yet on the department webpage. And while I was going over some notes, I noticed that there's a typo in one of my programs. So a file that's supposed to be labeled with the word Logit in the middle of it, OLOGIT, has instead a typo, and it's Oligit, OLIGOT. Okay, so I found little things like that I'll correct and repost. So the only errors, I'm sure, are tiny, inconsequential errors like that. Everything else is like picture perfect. Okay, so I'll share screen and start slides in a minute, but I wanted to first say a little bit about why we're doing the series and what our hopes are for the series in the future. So the main reason for having the series is that it will never be possible for the sociology department to offer enough formal seminars to cover all of the potentially useful quantitative methods that you might use in your career, even as early as in your thesis and dissertation research. And it's the best way to think about the courses that are offered in the department is that they create a foundation, and from that foundation, hopefully you can go on and learn new methods on your own, or possibly by taking a short workshop at professional meetings, or maybe taking advantage of online workshops that are hosted by various organizations, including ICPSR, the International Consortium for Political and Social Research, and so forth. And just to give you an idea of why you should think that way, nothing that I talk about in this session was offered in coursework in my graduate program when I was a graduate student. And in fact, most of the methods that I'll talk about had not been invented in the sense that there were published articles on them in sociological journals, and there was also no statistical software that would implement the methods. So I've learned them all subsequently. And the original methods courses that I had in graduate school did not cover even 1/2 of what today is covered in 631. And it's not because 631 as offered here is a more demanding course. It's just that what's expected is different now because the materials on it are more readily available. It's easier to teach certain methods now than it used to be because the available textbooks are better, the software is so much better, and so forth. And all that does is it just pushes the boundaries out for what you might consider using. Okay, well, I'm going to jump into sharing screen. Please know that feel free to interrupt at any time, ask questions, raise objections, ask me to clarify, etc. And I'll go back and forth. Let's see if all goes well, which it's not. Okay, oh, here we are. Okay.
It's working.
It just took a little while before it kicked in, and it confused me. I'm easily confused. Okay, so we're gonna talk about ordinal logit regression and fractional regression, with the focus on how these methods can be used to study or to investigate variables that have some kind of rank order and but are not exactly appropriate for standard methods like OLS regression. And ordered regression, we'll see, is used when we have a rank order variable, and fractional regression is when we have a quantitative variable that has continuous values, not categories, but it's bounded. It's got upper and lower limits, which causes problems for using conventional routines. So quick overview, we will talk about OLS regression as a point of comparison. And as a point of comparison, we'll look at simple or binary logit regression and multinomial logit regression, which is not so simple. And the jumping off point for multinomial regression, logit regression, is that was covered in 631, offered this spring. And so people who have taken 631 in the last few years, and normally you take that in your first year in the program, you would have been exposed to all three of these methods: OLS regression, binary logit regression, and multinomial logit regression. And then ordered logit and fractional logit has sometimes been covered in the past. It was not covered this year. And so there are a couple of assumptions here, and the assumptions are not intended to cause anybody to jump off, but for ease of conversation, I'm going to assume that people have heard about multiple regression and logit regression and multinomial, but you can ask questions about any of those methods, for clarification, or memories fade even if you've been exposed to these. And then we will be talking about measures that are going to be the dependent variables in the model. And these include proportions, which I didn't bother to put on the page because proportions are pretty familiar. And then there's an odds ratio representation of a proportion, and we're using OR for odds ratio, P for proportion. So P divided by 1 minus P gives you an odds ratio. If you take the logarithm of that, then you have what is called a logit, which is a logarithm of an odds ratio, and then logit for convenient expression. So we have an odds ratio transformation, and then we have the logit transformation of the odds ratio. That means you can go from proportion to odds ratio to logit, and then there are the reverse transformations that take you in the opposite direction. So if you have a logit score, you can go to an odds ratio by exponentiating the logit score, that is, raising it to the power of E, the base of the natural log system. And then once you've got the odds ratio, you can get back to a proportion by implementing the calculation of taking the odds ratio and dividing it by 1 plus the odds ratio. And those are just, in case you're following examples in this slide set or in notes that I've posted, those are some calculations to that may come in handy. So there are 4 categories of measurement that are typically recognized when we're doing quantitative analysis. And here we're focusing on the dependent variable in analyses that we might be undertaking. And so we could have a nominal dependent variable, which would be a variable where we can identify outcomes, but the only thing we can identify is that the outcomes are distinctive, and there's no notion of distance or even rank order. If a dependent variable has ordinal qualities, then it's got categories that we can rank, and but we're not willing to make distance assumptions about how far apart. There are some weak notions of distance implied because we are ranking them. So there must be some threshold that we're acknowledging that makes one category different enough from the other that we would not call them as having the same rank. But the distances are not presumed to be equal across ranks. An interval level dependent variable allows for continuous scores that are on a distance scale. It doesn't, an interval variable does not necessarily have a true zero, and that means that relative distance distinctions aren't meaningful. A simple way to think about that is the information contained in an interval variable is not modified if you add a constant to the values. That is, all the distance distinctions remain the same, even though the numbers change. The distances between the numbers all stay the same. But if you were to do relative comparisons, like take one score and express it as a ratio of another, those would all be changed by adding a constant, and that's not appropriate with an interval level variable. So that would take you to the next category, which is a ratio level, which is continuous with a true zero, and the distances support relative distinctions, so that if you are adding a constant, well, you wouldn't, because adding a constant would change relative comparisons. Anyway, these are the kinds of methods that we're talking about. We're going to be moving from nominal to ordinal to interval, and ratio variables are often also analyzed in the methods appropriate for interval. We're also going to distinguish between bounded and unbounded variables. And so an unbounded variable is one where, at least in principle, you can go to the sky, or you can go to the bottom of the ocean and below. Up, you can go up indefinitely, or you can go down indefinitely. So in principle, income is unbounded. Income can grow to the sky if you're Bezos, and I guess you're back from space today. And if Bezos were to put all his money into Bitcoin, and Bitcoin went into bankruptcy, you could have negative scores on income. And logarithms of ratios are unbounded, going up and going down, and a variety of other variables have that quality. Some variables are single bounded, so simple odds ratios are bounded on the lower end. They never go below zero, but they're unbounded on the upper end. And then, things like soccer goals, age, number of years of education, years since immigrating to the country, they're all bounded at zero on the low end, but they're open-ended on the top. A double bounded variable is something like a lot of inequality and segregation scores. They're capped at zero on the bottom and 1 at the top, or maybe they're expressed as 0 and 100 for the bounds. SES scores are bounded, usually 1 to 99. Likert scales, they're bounded 1 to 7, 1 to 9. All of these can be converted into a 0-1 range to make them all similar, but the key thing is they're all bounded. Bounded variables, as we'll see, cause problems for OLS regression, and it makes one of our major tools for performing analysis problematic. So I've prepared a little chart. 3 checks means good, 1 check means maybe okay if you're lucky. A dash means the combination is not appropriate. And what we see here is that if you have a nominal variable, you can analyze it a variety of ways with cross-tabulation and chi-square analysis. Maybe if it's a binary variable, just 2 nominal categories, you could do binary logit regression. 1 check means maybe you could do OLS regression with it, and that's called linear probability regression. And if you've got more than 2 categories, you could do multinomial logit. You might be able to do fractional regression if it's a 2-category variable. And then for an ordinal variable, ordinal logit regression is the only one here with 3 checks. A couple of the others are maybe okay if you're lucky. Interval variables, they would be handled with OLS regression down at the bottom if it's an unbounded variable like income. And if it's a bounded variable, then OLS regression only gets 1 check because it's compromised. But other kinds of regression might be available, including fractional regression and count regression. Ratio variables are similar. Okay, very, very quickly, if you want to look at these slides in more detail, just laying out the pros and cons of these analyses. We'll go really fast over these. Cross-tabulation and chi-square, you learn that as an undergraduate, and you could pursue it in advanced studies. It's easy to implement, pretty helpful for limited kinds of descriptive analysis. There are no estimates of effects, so it's hard to test hypotheses of effects of variables, and multivariate analysis is really difficult. So we usually move from cross-tabulation analysis into logit and multinomial logit analysis, maybe into ordinal logit if the variables have rank order. Linear probability regression is taking a 0-1 variable, which could be like a 2-category variable, and running OLS regression on the 1s and 0s. The main advantage is it's easy to interpret effects and it's easy to do it. The major problems are you can't do significance tests that are with valid, because the assumptions underlying it are not valid. And you can easily get bad predictions because it incorrectly assumes that effects of the independent variables are linear and additive. Logit regression is an improvement on some of that for a 0-1 variable. The assumptions about the error term are more appropriate. Effects are assumed to be nonlinear and non-additive, and those are the advantages. It's harder to interpret, so that makes it a little more demanding, and it's harder to implement, take specialized software, and because it's based on large sample theory, it's hard to do tests unless you have fairly large samples. I just repeated the comments on tabulation, cross-tabulation, and chi-square again, and then put them beside OLS regression. When we're looking at polytomous dependent variables, we could do cross-tabulation. It's got the same problems as before. We can't go very far. If we're using OLS regression, we don't have any options for analysis because OLS regression must at least assume some kind of rank order, and a polytomous dependent variable that's nominal doesn't have that. We could then turn to multinomial logistic regression. Then the error term assumptions will be appropriate. Effects will be estimated in an appropriate way that will presumably be nonlinear and non-additive. Multinomial regression effects are very difficult to interpret. Usually we have to do some kind of predictions to spell out what the implications of results are. And the coefficients themselves are very difficult to interpret except in simple models. The model itself is pretty difficult to implement. You need specialized software, and like all maximum likelihood procedures, it requires large samples to be confident about your significance test. If you move to an ordinal dependent variable, you can use OLS regression. That would be easy to implement and easy to interpret, but you would run into problems because the assumptions of OLS are not met, which means your statistical tests are suspect. And you can also easily make bad predictions because it will incorrectly model the effects as linear and additive when that's not appropriate. And it also implicitly invokes an assumption that the distances between ranks are known, and that's most likely not true. So a lot of problems, it's easy to do it, but it's hard to get people to believe the results. And you could use multinomial regression with an ordinal dependent variable. It would be a complicated model. If we go to the next, we could say use ordinal logit regression. That might be the preferred approach, but we could consider multinomial logit regression because ordinal logit regression makes some assumptions which may not be correct. In particular, the assumption about ordinal ranks being similar regardless of the subset of cases that you're looking at. So we could use multinomial logit regression to model an ordinal variable. It makes the analysis more complicated, and in the ideal situation, we could dispense with it and go to ordinal regression. And if we were to use ordinal regression, the assumptions are appropriate, effects are modeled as nonlinear and non-additive as they should be, and the effects will actually be quite a bit easier to interpret. There's another option, which is to use fractional regression, and I won't comment much on it because probably we would just go straight to using ordinal regression. If you have an unbounded interval variable, then we can do OLS regression using the scores as they are. The results would be easy to interpret and implement, and the equations would be easy to estimate. The OLS assumptions would be met. The assumption of linear additive effects would be appropriate, and we would only limit ourselves to the usual concerns about OLS regression. So there are occasions when OLS regression is just great, and birds chirp, rainbows are in the sky, and we're all happy. For this kind of variable, there are no other methods that are superior to OLS regression unless some kind of a problem has come up with our OLS estimation, and then we might turn to variations on OLS regression, extensions into weighted least squares, robust regression techniques, and bootstrap regression. So now let's get into the topic for today, where we've got a continuous variable that's double bounded. And any variable that's got an upper bound and a lower bound can be placed in a 0-1 continuum by applying some kind of a transformation. You simply set the scale to be 0 to 1 instead of whatever the original scale is, and map the original scores into the 0-1 scaling range. When you're modeling a 0-1 variable, you've got a basic problem, which is that an OLS regression will keep making predictions even beyond 1 or below 0 when that's an impossible outcome. And that can occur for many reasons, the most important being that the OLS modeling approach assumes linear additive effects. When that's not the case, the effects are actually nonlinear and non-additive. They're nonlinear because as you get close to the boundary of 0 and 1, any effects on the dependent variable have to stop. They have to slow down and then eventually stop. And OLS does not permit that. In addition, OLS error assumptions are not met, so all your statistical significance tests are compromised. And it's mainly a question then of whether you could work with OLS regression and get away with it. That's a practical question. There are some circumstances where if you ran OLS regression on a double-bounded continuous dependent variable, you would not necessarily make egregious errors. So an example might be modeling socioeconomic status scores, which are typically scored 1 to 99. That's bounded on the bottom and it's bounded on the top. You could wind up with OLS models that predict 105 or -10. That would be impossible. That would reveal that there are problems in the modeling process that are important. If those problems don't creep into the analysis, you might get away with modeling that variable using OLS, but there would be a better way. So the better ways would be to perform OLS regression on Logit scores, which means you're putting the original scores on a 0 to 1 scale and then transforming that into a Logit score. That will allow you to model the scores with the implications for the raw scores being kept in a 0-1 range, not getting out of bounds and being impossible. And you can also go to apply fractional regression methods to the same dependent variable. And we'll talk about that method in more detail in a minute. So let's see, trying to move forward. So let's get into ordinal logit regression. When would you consider using it? Your dependent variable needs to be categorical. It needs to have 3 or more categories. Otherwise, if it only had 2 categories, you'd use regular logit regression. The categories need to be rankable. If they can't be ranked, or if you have doubts about how they should be ranked, you should be using multinomial logit regression instead. And the distances between the ranks would not be known, or they can't be presumed to be known. And the usual assumption would be that if you had ranks 1, 2, 3, 4, the numbers 1, 2, 3, and 4 would represent equal distances if you applied, say, OLS regression to those scores. And if you can't assume that those distances really are meaningfully identical, then you would instead just treat those as ranks that are of unknown distance. And that would allow, that would make ordinal logit regression appropriate.
Dr. Fossett?
Sure.
What do you mean by distances? Like, how is that they cannot be equal?
Just stepped away for a second to close my door because I was on your dependent variable. Let's say that you have the variable we're going to be analyzing here to start with has 4 rank categories, and they're coded 1, 2, 3, 4, with 1 being the lowest category and 4 being the top rank category. And if we treated 1, 2, 3, and 4 as meaningful numbers on a distance scale, the distance between 1 and 2 is 1 unit. And the distance between 2 and 3 is 1 unit. And the distance between 3 and 4 is 1 unit. And all of those distances mean the same thing. They, somewhere we have a logic of measurement, and we're saying, I'm moving up 1 unit on this variable. And that 1 unit means something quantitatively. If you're in rank order, you could be moving up a category, and it might be very different in its implications for quantitative differences. Suppose my bottom category is everybody who's in poverty. My middle category is everybody who's middle class. My third category is people who are high income. And my fourth, which I define as not being a millionaire. And my fourth category is a millionaire. Well, the progression across those categories is quantitatively very different in terms of its implications for income. They're ranked, but the difference between poverty and middle class is not the same as the difference between being high income and being a millionaire or a billionaire. So that's what we're getting at. So in your database, it's very common, in your data set, it's very common to have a variable with scores that look like they carry quantitative information when the actual logic of the numbers, we would know from our measurement theory, is that it only represents rank difference, ordinal difference. Does that cover it?
Yes, thank you.
Okay, let's see. So we already earlier said that OLS regression has problems when we use it to predict rank scores, and it basically invokes assumptions that are inappropriate, and unless you're really lucky, things can go wrong. You could be lucky. There are times when rank order scores behave in a way that OLS results wind up catching what's actually happening reasonably well, but that's just good luck. You can't count on that, and you wouldn't know that they're working well unless you compared the results with results from more appropriate methods. So what could you do? Well, you could go to binary logit regression by taking your ordinal variable and collapsing it into categories. And what would the reason for that be? One might be because maybe you know logit regression, but you don't yet know ordinal regression. Okay. So the problem with that is that you're giving up information on the dependent variable. And if we did using that example I conjured up a second ago, we could do a dichotomy between millionaires and everybody else, but that's giving up the distinction between poverty and middle class. So that wouldn't be so good. If we made the distinction just poverty and everybody not in poverty, then we're giving up distinctions between middle income, high income, and millionaires. So everything comes at a cost, and there may be a benefit. The benefit here is simplicity. The cost is information. So ordinarily, if we can, we'll try to hang on to all the information we've got. So we would go to ordinal regression. I'm going to skip past this slide in the interest of time. And so here we are with ordered regression. And so what can we say about it? The dependent variable that we're thinking about is a set of categories. And that means the dependent variable is, well, let me see here. So the dependent variable is the relative distribution of cases. You could think of that then as a histogram for Y. And I'm going to skip down. So here's a histogram. We're not even talking about the dependent variable, but we're not talking about what it is, but these 4 bars right here that I'm waving the pointer over 1972, that's the dependent variable. It's not one numeric score. It's 4 separate scores. The percentage in category 1, the percentage in category 2, the percentage in category 3, and the percentage in category 4. All of those are being predicted simultaneously. That is the dependent variable. So multinomial regression is one way to predict that distribution. And if we run multinomial regression, we'll get a baseline prediction of what these bars would look like. And here I've run a multinomial regression, which is predicting 4 categories, and it assumes that there are no X variables that make any difference. So what you'll see is we have year here. That's a possible X variable. The categories, to make this, to focus on the actual variable, it's where white respondents fall on a scale of 4 categories where they indicate whether it's okay to oppose residential integration or not, racial residential integration. If you're in the top category, you're saying it's okay for whites to oppose integration. If you're in the bottom category, you're saying no, it's not okay. And if you run a multinomial model with no X variables, you just get a baseline prediction, and that baseline prediction is the relative frequencies as they occur in the full sample. So what we see here is the prediction at every year is identical. It's the same bar graph. The leftmost bar, which is whites saying that it's wrong to oppose integration. That's the most common frequency with almost 50% of the responses, and the other bars are lower. And it's the exact same set of bars all the way across. Now this is based on a multinomial, let's see, actually it says that's an ordered Logit prediction. Okay, that's a mislabel. That should be MLogit, so that's a typo in my program, or in my slides. I'll need to correct that. This is okay, no, I misspoke. This is ordered Logit regression with no predictors, and it predicts the same outcome all the time. Why? Because there's no X variable, so there's no basis for distinguishing between the respondents in the survey. And what is your best guess for predicting the outcome if you don't know any information on X's? Well, you would just guess the overall distribution on the 4 categories. So it would be just the sample proportions across the four categories of no, it's not okay, all the way over to yes, it is okay. If you add an X variable as the predictor, in ordinal Logit regression, the effect of X, if it has an effect, is to systematically change the bars. Now, to be clear, what you get are a set of coefficients. So here's a ordinal Logit regression without any X variables, and down here we've got a set of coefficients. We're not going to talk about them. We're just there they are. What is their implication in that model? Their implication is that the distribution across the 4 categories has a pattern, and that pattern is the same for everybody, because there are no distinctions being made on X, so there's no basis for saying that we would expect anything other than the basic pattern that we see in a simple cross tabulation, where we are tabbing the respondents by their answers on the question. Here we have an X variable of year, and year does have an effect on the attitude that whites have in response to the question, is it okay to oppose integration? And what we see is, just looking at one bar, let's take the very first bar, which says, no, that's wrong. It's wrong to oppose integration in a neighborhood. That was at a low value in 1972, and then progresses in a steady, systematic way to, by 1996, it's up around 70. So it goes from maybe 35% up to almost 70%. So people say it's wrong occasionally in 1972, and then they overwhelmingly say it's wrong in 1996. The thing about an ordinal Logit prediction is that the way the bars change is very structured. So the end bar on the left, if we have a negative effect, which in this case, as time goes by, people's opposition to regression, people's opposition to integration is going down. So that's a negative effect. That means the bar on the left will rise, and the bar on the far right, so in 1972, that's the lightest color bar on the far right, which I'm wiggling the pointer over, that bar goes systematically down. So that must happen in ordinal regression. The ordinal coefficient is moving the bar graph, taking the bar on the right and shrinking it, and increasing the bar on the left. And the categories in the middle will change systematically in between the way those two are changing. So here you can see a steady progression. The bars on the left grow, and the bar on the right falls. Okay, so come back to this point. If you could think about what the objective is, you're predicting the histogram, the relative frequency distribution of how people are distributed across categories. So it's not a single value, it's a set of 4 values, the set of the 4 percentages that define how people are distributed across the 4 categories of this ordered variable on opposition to integration. So the reason I stress the graphic here is that this is the best way to show people how a variable is having effects. There's no single coefficient that will give you the same easy to understand interpretation that this graph is giving. Like if we compare 1972 to 1996, what do we see? The number of people who's saying it's always wrong or never, it's very strongly wrong, that's doubling in its height. And the percentage of people who are saying it's okay to oppose integration, that's falling off the table. It's only maybe a third or a quarter in 1996 of what it was in 1972. In the ordered logit regression equation, the effect, let me see here, the effect of an independent variable will be a coefficient. That coefficient will not be easy to interpret. The sign can be interpreted, and the significance level can be interpreted. But the implications for a bar graph are not easy to interpret. So that is just something we have to live with. We have to know that to get the predictions that we see in this chart, we're going to need to first estimate an ordered logit regression, and then that regression will provide a basis for doing statistical tests. But when we want to assess the substantive effects, that is, the impact that X has on the dependent variable, we're going to need to look at predictions. And we could generate quantitative values that represent these bars, but it's also helpful to plot them, as I've done here. And then you can visually look at this and see if you think these changes are meaningful. So if we go to an equation, and here we have an effect, ordered logit. We find an ordered logit regression coefficient. The coefficient is positive. In this case, the variable involved is region, not year, but the positive effect is the fact that the sign is positive means we're elevating the bars on the right-hand side. And then we have a statistical test based on a Z ratio, the coefficient relative to its standard error. That's called the Z ratio. And then we have a probability value. So this is interpreted just like in OLS regression. And basically, z values above 2 are probably going to be significant at 0.05. You need to be a little more careful than just that rule of thumb, but as a rule of thumb, z ratios at or above 2 typically are statistically significant at 0.05. So 13 is a really high z ratio, and it's significant at 0.01 and even 0.001. And so we know direction. The values we're moving toward the higher ranks. We're elevating the right-hand side bars if you live in the South compared to the not living in the South, and it's statistically significant. If we're trying to make sense, let's see. If we're trying to make sense of the predictions, we can do predicted value tables or we can do graphs. In most work, when I'm trying to make sense of a prediction, I generate a graph because that helps me see what's going on. Okay, I know I'm moving fairly quickly. I'm skipping over slides in some cases because you can go back and take a look at these slides. What I did with a couple of slides here is I contrasted analyzing this variable first using multinomial logit regression, which would have been covered in 631. And then I do the same thing using O-logit regression. I also show in these slides how you do calculations by hand that will reproduce the coefficients from the logistic regression. So you can see that what the regression procedure is doing is nothing magical at all. It's just representing the simple, let me just say this more carefully. We start with a simple tabulation of how respondents are distributed across the categories of opposing, is it okay to oppose integration? Strong no or firm no to firm yes. Here's how people are distributed by cases in the data set. Here's their percentage distribution, and the percentage distribution would be the basis for a histogram. And we're simply saying, well, how can we model these percentages? Well, here in these notes, it shows that if you take the numbers up here, do some calculations using these numbers, and then take the logit of that calculation, you get a particular number, and then that actually shows up as a coefficient in the ordered logit regression. And the purpose of the demonstration is just to show these are not magic coefficients. They come right from the data. They can be understood, and then that helps us understand how we go from coefficients back to making predictions about what we would expect would be happening in this tabulation if we could generate a tabulation like this for respondents who have particular combinations of the various X variables in the analysis. Anyway, so I'm going rapidly through these. You've got the slides that you could go to, and then there are lengthier notes documents that I've provided, plus also example programs that run these regressions and show and provide commentary on what the coefficients mean and how to get implications out of the analysis.
Dr. Fossett?
Yes.
So in the previous slide where you have cut 1, cut 2, and cut 3, why don't you do a cut 4 for your last category?
Why isn't there a cut 4?
Exactly.
Yeah, well, because each one of the cut points is referring to the transition between two categories, and that only occurs 3 times. So you move from category 1 to category 2. So this coefficient for cut 1 is capturing that. And that's getting at, do you have more people in the bottom category compared to the next to the bottom category? So that's what cut 1 is about. Cut 2 is the comparison between the number of people in category 2 and category 3. And then cut 3 is the comparison of category 3 to category 4. And at that point, you're out of all the possible transitions. So it only takes 3 cut points to capture the pattern. If you don't have an X variable, let me see, here we are. Here's the equation without an X variable. The predictions that come from this equation will exactly reproduce this table up here. And that's shown in the calculations, because what it does is these little notes right here show you how numbers from this tabulation can be turned into cut point values. Here's how they're calculated by hand. And then they show up in the actual logit regression results. And the hope is that you would see, oh, these logit regression, these ordinal logit regression results are a way of quantitatively representing the original cross tabulation. The original cross tabulation doesn't have an X variable. It's just tabulating the dependent variable. The beauty of the ordinal logit regression procedure is that once you capture the basic structure of the dependent variable with these cut points, you can now introduce X variables like region or time or education or gender or age, and things may shift across cut points. And so here we have the independent variable of South being added, and this variable here now has an independent effect. The cut points are still here. They're capturing how people are distributed across the 3 cut points. 3 cut points to capture 4 categories. And then South is telling you how people in general in the South versus the non-South shift up or down across all of the categories. So not one category at a time, but across all 3 of the cut points. So the literal interpretation of this coefficient is that because we're focusing on the South, and South is coded 0, 1, 1 if you're in the South, 0 if you're not, that means that these cut points generate a relative frequency distribution for people in the non-South. And then for Southerners, we add this logit coefficient to all 3 of these separate cut points, and we get a new set of cut point coefficients for the South. Those coefficients will imply a new frequency distribution. And I'm moving rapidly when that's only a few words, but it's a lot of meaning. And so let's see, I guess I haven't done this yet, but I will now mention we have an open date on the schedule Thursday, which got canceled. And I would be happy to come back on Thursday and follow up on any questions that anyone might have. And the only thing I would need to get me to show up is that somebody else is going to show up. So if anybody would like not to have a repeat of this presentation, but a chance to ask more detailed questions, maybe after you've seen the slides, maybe you even go and look at the other materials that have been made available. If anybody would like to come back on Thursday and continue with a review of any of this, or with some questions about issues that come to your mind, as you go over the material. Email Peggy and Luz, or Peggy or Luz. Let them know that you would plan to show up. They'll let me know, and I will show up.
I'm going to go ahead and say right now, this is Bonsa, that I would show up.
There's one. Okay. I don't know.
Me too, actually.
I'll probably show up for one, but I'd feel better if two. So in this slide, I'm just showing that the baseline model of the M-logit equation and the M-logit being multinomial logit, and the baseline model for O-logit, ordered logit, neither one of those models have, I'm sorry, let's see. These models have no X variables. And what they do is they generate predictions for the proportion of cases in each of the 4 categories. When there are no X variables, the ordered logit and M-logit, multinomial logit and ordered logit, they generate the same exact predictions. That's worth knowing. Because what are they doing? There's no X variables to say that the expectation would be any different. We don't know, even if we know that people differ on gender, time, age, education, etc., that's not in the model. So there's no basis for establishing that those variables would make a difference. So we predict what's going on based on the simple original tabulation of the dependent variable. And so note that we're not making a prediction about a value for a single person, because a single person can only be in one category. A single person will either be a firm no, a mild yes, or a firm yes, based on their original response. But our dependent variable is our expectation. That expectation is represented by the histogram, where we think it's most likely they would, with 0.46 probability, it's most likely they'll be in the firm no. It's less likely that they'll be in the firm yes at only 13%, or probability of 0.13. When we add an X variable, the predictions are no longer identical, although they happen to be pretty close here. So with an X variable in, and the X variable is south, if you are in the south, it has an effect, and the predictions here are now slightly different in the ordered logit model, but they're only showing up as different at the 3rd decimal place. Now, what that means is that the ordered understanding of the dependent variable is reasonable. That is, if we're treating the steps across categories as being modeled well, that is, if our understanding of the ordinal nature of the variable is correct, and that ordinal ranking is pretty much the same in the north and the south, then the ordered results and the multinomial results will be very similar. If the multinomial results were substantially different, it means that the ranks mean something different in the north and the south. And that could be true. That does not appear to be the case in these data. And that's why we might compare the multinomial logit and the ordered logit predictions. What does this slide say? This is a technical issue which I'm going to gloss over right now in the interest of time, and it's treated more carefully in the notes document anyway. Okay, what I was just doing does relate, what I was just discussing does relate to this slide. The ordered logit model is a special model that fits under the multinomial logit model. The multinomial logit model can capture a wider range of variation in the respondent answers to the 4-category question. The ordered logit model imposes the assumption that this is ranked, and that if X has an effect, it's going to systematically move people up and down ranks. The multinomial model does not assume that. The multinomial model allows for the possibility that if somebody changes based on an X variable, they could jump from category 3 to category 1 and skip category 2. The ordered model says, no, they're going to move in a progression. Folks who would have ordinarily been predicted to be in the lowest category would be moving into higher categories in a steady progression, not in weird patterns. The multinomial model doesn't impose any assumption that you would move through a rank sequence, so it allows for crazy jumps across categories, which would be relevant and completely appropriate if it were a nominal variable. So somebody, say, moving across categories of religion, you might have 4 categories. Well, you don't have to go through all 4 categories to make a progression. You could jump from Catholic to Protestant without necessarily going through the category of being Jewish. Ordered logit regression says, hey, this is not a nominal variable. This has order to it. People will tend to progress from low to high or from high to low, depending on what the effect of the X variable is. In the case of a variable that we think is rank ordered, we hope that the ordered assumption is appropriate, because if it is, the ordered logit regression is a much easier regression to understand. The ordered results are easier to visualize, they're easier to describe, and they're much easier to discuss. Because you can say things like, education moves people in the direction of saying opposing integration is wrong. Being female moves people in the direction of saying that opposing integration is wrong. That's an easy, parsimonious description of effects. And let me see here. I thought I had something I was going to say something about. If we were doing multinomial logit regression on these same outcomes, if that was necessary, it would be because the pattern would be much more complicated. So you might wind up saying, folks who are, if you're a woman instead of a man, you tend to jump from strongly oppose integration to strongly, you move from, say, strongly opposing, saying it's okay to strongly oppose integration, to not at all okay, without crossing through the middle categories. And then gender might have the opposite, more complicated effect. Your hope is that none of that's going on. And that hope can be tested. So that's the point of this slide. The point of this slide is that if you're assuming ordinality and modeling the data that way, that would be convenient. It's much easier to discuss. It makes a lot more sense if you truly believe this is a rank order outcome. And you can test that by running multinomial regression, comparing the results to see if the multinomial model improves your ability to predict the distribution of cases across the 4 categories. One of the notes document that I posted tells you how to do that test. Some of the example programs show you how to implement that test in Stata. Okay, I'll leave that as it is, and let's say that we've done that test. It tells us that we're okay. Ordered logit regression is the way to go. And then here's some comments on how do we make that judgment. So the headline here, how does one assess ordered logit model fit? Well, if we go back and look at the results, let me see. Here's an ordered logit result, and it's got something here that people look at a lot because it's reported by almost all ordered logit software. It's called pseudo R-square, and it's got a number. Here's what I'm going to advise. Don't bother looking at this. I never look at this number. I'm going to come back to my point here. The pseudo R-square statistic, I think, is very well named because it is really pseudo. So pseudo is not a compliment. So if you're pseudo ethical, then you're probably not ethical. And this R-square is not at all comparable to R-square in OLS regression. And I regret that for whatever reason, people invented this statistic and software reports it. I never look at it. I never learn anything useful from looking at it. I know people who do look at it, and when they tell me it means something, I ignore them. And if they were pressed to tell you in substantive terms why you should care about it, they would have a very hard time. And let me be blunt. Come down here. Tests of theories almost never are decided by pseudo R-square. If you have a theory that says gender makes people more tolerant and therefore less likely to oppose integration, you will not test that theory by looking at pseudo R-square. You will instead just look at the effect of gender and see if it shifts the distribution right or left. If gender reduces opposition to integration, it's going to shift the distribution left. That means it's going to have a negative effect on the ordered outcome. So when do we care about model fit, and when would pseudo R-square be relevant? Well, it would be relevant if all we cared about was prediction. It's not very often in journals that you see an article where the analysis is only about prediction. Typically, to get an article published in a journal, you're testing a theory or advancing our understanding of how various independent variables have consequences for things that we care about. And prediction is rarely what we care about. What we typically care about most is whether things are moving in various directions, and we could either think about that as giving us insights into whether theories make sense or not, or we could think about it as having relevance for policy that we might implement. Things can have low R-squares and still be relevant for policy. If everybody has low education, in your sample, low education will not explain very much income. And you might look at, say, Appalachia in 1920 and say, well, the R-square predicting income is low for the sample of people in Appalachia. But if your theory says, well, if you educate people, they'll be more productive, they can do work that would justify higher incomes. And if you implemented a policy of upgrading the education in the region, you'd get people out of poverty. They'd go into higher paying jobs. And so what does R-square help you with? Nothing. It doesn't give you any insight. It's the effect of education that matters, and that would drive your concerns about policy, and it would drive your evaluation of any theory about education as having effects that are meaningful for fighting poverty, or in this case, having implications for who opposes integration and who accepts residential integration. Oh, let's see. We've already gone an hour and beyond, so I should, and we've only we're just getting through ordered logit regression. It does work out that a lot of the implications or a lot of the ideas on the table carry over into fractional regression, so we can cover it a little faster. So anyway, what will I say here additionally about this particular slide? There could be an occasion where you compare ordered logit regression with multinomial regression with the same set of predictors, and the multinomial model fits better, and the fit is statistically significant. Here's what I would say. You might still go with the ordered logit model. And the reason for that could be that you want parsimony. And, prediction success by itself is not a strong selling point for a model. Let's see, this last point will help. Sometimes models that predict well generate predictions that don't make any sense, and we would be well advised not to believe those predictions. So predictions that are well justified by the theory that motivated the analysis in the first place are easier to accept. Predictions that are successful in a given analysis could be accidents of chance. And one of the ways that we could think about that is that if we did a new study, got a new set of data, if the multinomial predictions were kind of in the first analysis, if they didn't really make a lot of obvious sense to us, if they kind of hopped around, and it could be they're really just hopping around and fitting idiosyncratic patterns that occur in one sample. So you should only believe them if you really do think that when you do the next study, you're going to see the same pattern. And often that will not be the case. Okay, let's see. We could start, well, I guess we're over an hour. At this point, ideally, we would be in question and answer and discussion. I'm going to go fairly rapidly through fractional regression so that we can have some time for discussion without running on too much longer. And like I said, I'll be happy to come back on Thursday if anybody else shows up, and we could talk about things that get glossed over here. So how does fractional regression compare to ordinal logit regression? The main difference is we have a continuous variable with a scale instead of a categorical variable with ranks as our only distinction. And the reason that fractional regression is preferred here is because we believe we know something about the quantitative scale that's underlying the measurement. And so it's a meaningful scale. It's moving us toward an upper boundary and toward a lower boundary as we move from high to low, and the steps are quantitative. That is, if we're moving from 0 to 0.2, that distance move of 0.2 scale units is the same as moving from 0.8 to 1. And if we think that a given x variable has that effect, it wouldn't matter where we start on the scale. It would be taking place as long as the x is changing. That would not be the case in ordered logit regression, because moving from one category to another might occur in a different way. That's captured in the cut point coefficients in the model. So fractional regression can handle a variable with a scale, and it's a model that makes stronger assumptions about how the world is working. It's working in a very predictable, continuous way, and the particular variable in question does have an unusual quality. It stops at a boundary. A classical example would be a proportion. Proportions they can't go above 1, they can't go below 0. And then there are a lot of measures that are scaled in a way that they vary between 0 and 1. The Gini index of income inequality goes from a low of 0 to a maximum of 1. Segregation index score go from a low of 0 to a maximum of 1. If we apply OLS regression to those, we're going to run into problems. OLS assumptions are going to be violated, so our significance tests are unsound. OLS regression assumes that an X variable will have the same linear additive effect no matter what, and that's not going to be true, because once you approach a boundary, in reality, you can't go above it. And so the idea that an X will always produce an equal size increment is just wrong. If you're already at the boundary, you have to stop. Well, fractional regression can handle that. This slide is saying that there will be times when OLS regression will be okay, and there are ways you can check on that. You should never assume it. In the past, like back in the 1960s, people would assume it because nobody had invented ordinal or fractional regression at the time, ordinal logit regression or fractional regression, so they would just run OLS regression. Since then, we've got better tools, and you wouldn't be allowed to do that, and you shouldn't be allowed to do that because a lot of times the OLS results will just be flat out wrong. How would you know when they're wrong? Well, you do it the right way, that's technically more demanding, and then you do it with OLS regression. And if the results are the same, then you can report in a footnote that you did it the right way, and you did a whole lot of work to be sure what the right answer is. And then you discovered that the same results can also be represented in OLS regression, and you might do that in your presentation or your paper for convenience, not because it's the right modeling choice, but because it's convenient for discussion and description. So punchline, especially for dissertations, master's theses, papers for publication, papers presented at conferences, you need to tell the audience, you know what the right way to do things would be, and that you followed that path. And then if you choose for convenience in a presentation to use a simpler method, you state very clearly that you're presenting those results only for convenience, not for determining what the truth is. Not that we actually always know the truth, but okay, I could say a little bit about the way fractional regression is estimated. It's like this slide is about technical stuff. Let's just say for our needs today that there's a modeling procedure that's available. It's something like OLS regression on steroids. It's a fancier version of regression, which is more sophisticated and can handle more complicated patterns than can be handled with OLS regression. The most important distinction is that when we make predictions for the dependent variable, the predicted means are always going to stay between the boundaries. So we're never going to have a problem of making predictions that can't occur in reality. In order for that result to be accomplished, the predictions will follow what is known as a logistic S-curve. And let's see here. I'm trying to see if I can, let's see. Luz, what's on your screen right now?
The slides.
The slides, okay. So I've got to I've got to screen share a different way. I'm going to, and now?
The bamboo paper, so you're good.
Okay. And the S-curve prediction that we're talking about, here's our X variable, here's our Y variable. Our Y variable has a high value of 1, a low value of 0. That might correspond to another scale, maybe SES, that goes from 99 to 1, but we have rescaled it to be 0 and 1 on the bounds. A positive effect of X, would follow an S-curve. It would approach the upper boundary but never go above it. It would approach the lower boundary but never go below it. And to accomplish that, it has to follow a progression of change that in the middle is fairly steep and almost linear, but elsewhere follows a curve. And the curve allows the effect to diminish as you approach a boundary, either on the high side or the low side. A negative effect would be an S-curve that just goes down instead of up. Okay, so that's what I mean. And this particular shape, it's got various names. It's sometimes called a sigmoid shape, sometimes called a logistic shape, logistic curve. It means that you start off gradually at the boundary and then move down slowly, and then you accelerate, and then you begin to slow down, and then it becomes flat. That's what an S-curve would mean. And back into the document. I'm going to gloss over the methods that are used, and let's go straight to getting some results. A simple fractional regression with no independent variables will give you a single coefficient. That single coefficient is a Logit coefficient, but it's not your traditional Logit coefficient like in binary Logit regression. It is the Logit for the predicted mean of the variable that ranges from 0 to 1. And then what I mean by that is explained down here. The fractional regression constant here of minus 0.65 is the Logit for the predicted value of the mean of the 0, 1 continuous variable. And how do you get from a Logit prediction to a mean on a 0, 1 variable? You first, you go from the odds ratio, you get the odds ratio by exponentiating the coefficient, raising e to the power of minus 0.65. That gives you an odds ratio. And then you convert the odds ratio using this expression, and it gives you the value of y, 0.34. And what the Logit, what the fractional regression has produced here is a prediction of 0.34 for the mean of the variable that scored 0 to 1 with continuous measures. So 0.34 is actually a possible value. So it's not the odds ratio of being a 1 or a 0. It's the actual predicted value. On this measure, you can take a value of 0.34, and that is the predicted mean for people in this sample. And here's a regression, fractional regression with a whole lot of predictors. And what's being predicted based on your values on the X variables is going to be a score ranging from 0 to 1 for one individual who's maybe older and in the South and male and lesser educated. Maybe their score on this outcome is 0.7. That would be the predicted value. And then for someone else who's in a relatively recent time frame, they live outside the South, they're female and they're young, maybe their predicted value would be 0.3. Fractional regression can make those predictions. And in the process of making those predictions, it will be in a framework where statistical testing is justified and where the resulting predictions will always be inside the 0-1 range. Those are important points because the alternative is we could take the same dependent variable and run an OLS regression, and we get the same set of coefficients, or we get a set of coefficients for the same variables. And this is much more familiar. We're predicting the same scores on Y, but even though these two sets of results look superficially to be the same, the OLS regression results, the assumptions for OLS regression are not met. So even though significance tests are reported with T ratios and P values for T ratios, those can be wrong. They can easily be wrong because the assumptions of regression are not met. And the predictions coming from this OLS regression, predictions of Y, can be higher than 1 if things have gone wrong, and they could be lower than 0 if things have gone wrong. So in this particular example analysis, we did the regression using OLS regression, and then we did the regression using fractional regression methods. We got predictions from both models, and I've plotted them against each other. And what we see here is that in this particular example, the OLS regression results were not too bad. And we see that the plus symbol is plotting the OLS results against itself, and that just makes a straight line running in a diagonal from 0 toward 1. And then the circle points are the values that are predicted by the fractional regression. And for a big portion of the curve, the two sets of predictions are about the same. And it's pretty much on a straight line. So I said curve, but a straight line is a kind of special curve. We do see an area where the two predictions are separating. When this occurs, there's a very simple rule. The fractional regression results are probably more correct, and the OLS regression results should be discounted. They should be ignored. They're probably wrong. And, the big story here is that for the most part, the two approaches are giving you the same answer. And, if you chose to, you might say, well, I'm going to not worry about this area down here, and I'm going to talk about the OLS regression results. And as long as you say, I confirmed every finding that I'm going to discuss using the right method, but for presentation, I'm going to talk about the OLS equation because it's easier to discuss, you might be allowed to do that. A reviewer in a paper would insist that you tell them the correct story before they would let you ever talk about an approximation story based on OLS regression. Now I'm going to show you where results are quite different. So if you download the slides and look, there's a brief description of what's being modeled, and there's a longer description in a notes document that I posted on fractional regression. But the key thing is the same kind of graph, and right here where I'm drawing a little straight line here, these are all predicted values that go far above 1. Those are based on OLS regression. Those are impossible values. They can never occur in reality. The OLS regression predicting the scores on Y that go from 0 to 1 are mispredicting in a very dramatic way. They're wrong, and they're highly misleading. If you move from here to here, oh, that's not, okay. I headed off in the wrong direction. So just basically, the fact that there's a difference between the points that are plotted in the S-curve and the points plotted on the straight line shows that the fractional regression results are far superior. We've got very wrong predictions, and this is the way predictions mostly go wrong with OLS regression. They go wrong when you get close to the boundary. When you're in the middle and not by the boundary, not by 1, not by 0, OLS regression and fractional regression tend to agree. Let's go to another example. Over here, we're very wrong with OLS regression with impossible predictions that are below 0. And over here, we're very wrong with OLS regression with impossible predictions that are above 1. Okay, moving to another, this is a whole series of examples. This is a different city. It's the same basic modeling process. Very wrong predictions there, very wrong predictions there, very wrong predictions there. In every case, OLS is fundamentally wrong. It's wrong in major, obvious ways. It's also wrong in more subtle ways.
So, Mark, you're predicting S, right, in these? In these graphs?
I'm predicting a dependent variable
Mm-hmm.
that is scored from 0 to 1.
Mm-hmm.
And I want to correctly predict. So the value could be as low as 0, could be as high as 1. It could be 0.2, it could be 0.5, it could be 0.7, it could be 0.9. I want to get those values right. If I'm right here, the fractional regression has predicted a value of about 0.99.
Mm-hmm.
The OLS regression has predicted 1.1. It's off. Well, actually, look at the scale. It's predicting 1.2 in terms of a percentage value. If that was an SES score that goes from 1 to 99, and then I modeled it as a fractional regression, so I rescaled it to be 0 to 1,
Mm-hmm.
I would be mispredicting status. So this prediction here would be to say that the status score is 99. The 0.99 would correspond to an SES score of 99. And the OLS regression is predicting a status score of 120, which is impossible.
Mm-hmm.
And it's impossible by 20 points.
Mm-hmm.
And the same thing down here. We're getting a negative 20 prediction when it should just be a prediction near 0.
Mm-hmm.
And there are other more subtle ways that this is all going wrong. That would take more time to explain. And I'm just going to say the fractional regression model makes the assumption that effects are nonlinear and non-additive. Nonlinear is easily seen here in the S-curve. And the non-additive is a little harder to explain based on the picture, but it can be explained in words. let's say you have a set of values on the x's, which puts you right where I'm wiggling the pointer right now.
Mm-hmm.
And then there's another x. And that x has a positive effect, which would presumably move you higher. Because the other x's have already placed you very high, you simply can't go much higher. So if you're that respondent with that set of x's, there is no way this additional x can push you any higher.
Mm-hmm.
You're already at almost 1. However, if your values on the other x's were putting you here in the middle of the y range, if this additional x is incremented, you can move up a lot. So that is the non-additivity. That is to say, the effect of a given x will depend on the other x's. It's not always the same. That makes the effects more complicated to understand and to explain. It also makes the OLS effects very wrong. And, it's easier to explain the OLS effects. They just happen to be wrong. So you've given a very easy to understand explanation that is way wrong. That's not a good situation. You just had your dissertation rejected. That's, of course, not going to happen because your committee will guide you toward a successful dissertation. I'll tell you what, let's see. I will stop. Let me see here. Trying to clear a few things. That was the end of the slides by the time we got here. I'll stop sharing for a moment. I posted discussion documents which are detailed. Couldn't have possibly reviewed them in a short amount of time. Went over slides that tried to condense the material, and we've still gone over an hour and a half. So we covered a lot of ground, glossing over many things. So that, let's back up and say, how do we think about these kinds of discussion presentations? We don't expect that you'd be coming away thinking, oh, now I'm an expert on ordinal logit regression and fractional regression. That's not the goal. And if that were the goal, we would have failed. That's not going to happen in even an hour and a half of presentation. What may have happened is that you'll be alerted, hey, there's a couple of methods out here that are worth knowing sometimes. You could have a dependent variable in your dissertation or in some paper that you're working on, some analysis that you're conducting that has the properties of being a ranked ordinal variable. And you're trying to understand how that varies with characteristics of respondents based maybe on, a variety of characteristics. There's some ranked outcome. Maybe it varies by race. Maybe it varies by gender, by age, by region of residence, by political persuasion, you name it. And you're trying to understand that, model it, test theories about it, and so forth. What would be the right way to do it? Well, hopefully from this presentation, you know a potentially good choice would be ordered logit regression. Do you know how to do it? Well, probably not. But you've got some materials you could go back and look at. And then maybe you could chase down some readings referenced in those materials, and you'd have some examples that have been laid out. And there's a bullet list that would give you a little bit of a guidepost for why you want to focus on ordered logit regression instead of maybe doing OLS regression. So you took the required course 631, you learned how to do OLS regression. You say, I'm the old joke, a kid with a hammer thinks that everything's a nail. You learned OLS regression. We're going to analyze everything using OLS regression. What do we learn from this presentation? Yeah, you could do that. You'll get results. The results in principle could be easy to explain, but the results would also be wrong. And they could be very wrong. And how would you know whether or not they're right? You wouldn't. And the only way you could know they're right is to go back and do it the right way, and then using ordered logit regression, and then compare that with results obtained by OLS regression approximation. Okay, so you may, from a presentation like this, only pick up a few rules of thumb. Oh, here's some things I should worry about. Here's some procedures I should maybe consider using if it's your dissertation or an important research project that you're working on. It'll be worth your time to invest in learning that procedure. And if these notes that are available as posted aren't enough, you could go chasing back to other materials that would help. Or maybe find somebody who's learned the procedure, buy them a cup of coffee or buy them a beer, sweet talk them and get them to teach you the method. I was working with graduate students in my graduate program to learn log linear methods. We didn't have any professors to teach us because log linear methods were brand new. There were no courses being taught. None of our professors were doing log linear regression, but they told us, oh, here's a paper you could read. So we went and read it. We literally bought each other beers, and we said, okay, you read this paper by Goodman. It's a really nasty, hard to understand paper. You're gonna master it. You're gonna come back and teach the rest of it. I'm gonna go over here. You're gonna buy me a beer, and I'm gonna learn how to run this software that was created to estimate that model. Between us, we taught ourselves the method. My first paper was an ASR paper using log linear methods, and it came out of a graduate student-led workshop on how to learn the method. This could happen to you. It has happened in our department here at A&M in the past. Graduate students working together have learned methods that weren't being taught in the courses that they're taking. Like, the good thing about methods is if you have enough time, you probably can master them. They're not magic. Beneath each method is some rationale. Beneath each method is a set of procedures you can follow. Associated with each method is a logic that you could come to understand. You could understand what the benefits are. You could understand what the limitations are. And then eventually you can also get some practical experience. And even though it's never taught in a course, you wind up using it in your dissertation. It gives you a superior analysis, and it increases the chances maybe you could publish your results and make contributions to knowledge, thereby making the world a better place, in which case you would go to heaven instead of hell when your dissertation is done. So I don't know. I'm an atheist, so I don't believe in either heaven or hell. But I would prefer to go to heaven with a good dissertation than to go to hell with a bad dissertation. Okay, so the presentation's over. Some people are still here. I haven't run everybody off yet. So if anybody has questions, feel free to wail away. I actually have a meeting at 3:00, so the discussion portion will be limited to about 10, 11 minutes, but we can use that time, and then I'm gonna have to break away.
I unfortunately have to hop off, but I will definitely come back on Thursday if we do meet. So
that'd be great. I heard you ask earlier, were we predicting S?
Mm-hmm.
I think I know why you phrased the question that way, and I could talk about that a little bit on Thursday. So the answer is that the analysis was kind of in that direction.
Mm-hmm.
It wasn't literally predicting S, but it could have been, and it was definitely related to your interest in that.
I'm really hoping that I haven't done everything wrong so far, because I've just used OLS.
Well, there are some punchline here. That sometimes you can do it, quote, wrong from a technical point of view,
Hmm.
but get findings that in fact are substantially correct. So, OLS can be an inappropriate method, yet still reveal the same thing that you would find using the correct method. And, if you know that, and if you have, from discussions like this, some appreciation for when to be most worried and when to be less worried, you start kind of getting radar for knowing when to worry a lot and when to forge ahead. So, like little dirty secrets that we can tell. Most of the time when I run fractional regression, the OLS results hold up. But I never know for sure until I run fractional regression.
Right.
And so if I send it off to ASR or some other, top journal, and a reviewer looks at it, they're going to say, why are you showing me this OLS crap? How would I know if that's right or not?
Mm-hmm.
I could, in a footnote, say, I did it with fractional regression. It reproduced all the same findings here. And I have chosen to present an approximation method for convenience.
Got it.
Well, at ASR, that's probably not going to fly. They're saying, hey, our audience is very sophisticated. We're going to just present the correct, technically sophisticated results. But if you were presenting to an audience without that background, you might use the OLS results and feel okay because you'd already confirmed and validated everything.
Well, I think I'm going to run everything again and compare the two, and like you said, see how wrong I am.
I skipped over there was a slide there with a rule of thumb, which I skipped over, or I didn't say it out loud. If all your predictions are in the range of about 0.2 to 0.8, or if your original score is 0 to 100, in the range of 20 to 80, the odds are the OLS results and the fractional regression results are going to be very similar. That's
true, because on the graphs that you were showing, I mean, it's affected in the tails. I guess I put more in the ceiling, yeah.
Yeah, OLS goes very wrong only when it's at the boundaries.
Okay.
In the middle portion of the scores, the 0.2 to 0.8 portion of the scores on Y, OLS typically will get those about right. There will be some nuances about the statistical tests and thing, but with large sample size, that will become unimportant. And the results, even on significance tests, will wind up being about the same.
Okay. So the command in Stata is just frac reg?
Yes.
Okay. Because I saw frac GLM as well, but.
Well, there's the GLM, frac reg, you could think of it basically as a programming convenience it's actually implementing the GLM model.
Oh, okay.
Yeah, this is true for so many things, that what looks like a procedure is just actually some computer software that makes your life easier. You could run the GLM procedure. My notes explain this and it demonstrates it in some of the programs. You could run the GLM estimation procedure. You'll see that you get identical everything. And what frac reg does as a procedure is just saves you from having to learn the convoluted syntax of the GLM procedure and use all the esoteric options it requires, because frac reg knows what to do.
Okay.
Yeah. So
Thank you.
Frac reg is relatively new. It's only been around for a couple of years. When I first saw it, I kind of going like, well, dang it, I spent all that time learning GLM and now I don't have to. It's like.
So if you're late to the party like me, I get to benefit from.
Well, it's, you know, when I was a kid, we walked to school uphill in the snow both ways, and people have it easier now. So I guess I should feel bad about that. No, I've got it easier now too, so I'm okay with that. I'm happy to see the software making the world easier than it used to be.
Thanks again, Mark.
I'm glad you were able to drop in.
Me too. Bye.
Bye-bye.
Thank you, Dr. Fossett, for everything. I hope to see you on Thursday then.
Okay, cool. Well, then I'm going to go ahead and say goodbye, because that'll give me 2 minutes to get ready for my next hour and a half meeting.